Hey guys! In today's video, we're going to be looking at Chapter 8, Lecture 18, Learning Objectives 3 through 5. So we're going to be looking at the proper way to draw a Lewis structure. We're going to be looking at electronegativity, and we're going to be looking at charge separation. So when we make a bond in a covalent substance, so bonds in covalent substances, the goal is to get that substance to get octets for all the atoms within there. So our goal, octets for all. There will be examples where we will not try and do this. For instance, hydrogen, helium. Hydrogen and helium are good already. They've already got their noble gas configuration, or in the case of helium, or in the case of hydrogen, they only need one electron to get to that noble gas configuration. So they're not going to try and get an octet. They're only going to try and get 2 electrons, as that is what their outer shell will hold. But when we're talking about most others, we're trying to get an octet. So octets for all the atoms. And it can do this in covalent bonds by sharing electrons. So when 2 nonmetals share electrons, they both get to use those electrons to contribute to their octet. Okay, so we could have, for instance, if we have 2 nuclei, we have what's called the inner nuclear axis. Is right here. And that's where our nuclei kind of sit, is right there. And then in between the inner nuclear axis, in a bonded pair of electrons, or in a bond, we have 2 electrons, where generally the electron density is between those 2 atoms. So the 2 electrons will be shared between those 2 atoms, both of them getting closer to a octet. The bond length is the length between these 2. And we call the bond length, it's going to depend on attractive and repulsive forces within the atom, or within the atoms within the bond. So the length depends on the attraction between the electrons of one atom with the nucleus of the other, and it also depends on the repulsion of the electrons of both atoms. So our electron-electron repulsions. Along with proton-proton or nucleus-nucleus repulsion. Okay, so the bond length itself is the balance between attractive and repulsive forces. Okay. The way that we show these bonds within a molecule is with a Lewis structure. So the bonds, those sharing of electrons, are depicted within a Lewis structure. A Lewis structure is going to show all bonds and what types they are, along with any lone pair electrons, and then of course the atoms that make up the molecule. So a Lewis structure of a molecule contains the molecule's atoms, so it's the molecule's atoms. It also includes all the atoms, electrons. So, well, specifically valence electrons. So no core electrons. So within here, our electrons can be as bonds, so pairs of electrons, or as lone pair electrons. Again, these are in pairs, but these are non-bonding electrons. So they will not be in between two nuclei on the internuclear axis. So those are the two we generally look at. We can also have radicals. So if you've ever listened to any infomercials, you've probably heard of radicals. Radicals are unpaired electrons. Okay. And again, our goal here is to try and get a structure where the atoms within there have an octet, except for things like hydrogen. Okay. So we can look at something like NH3. If we were to draw NH3, we could start out actually with our Lewis dot structures. And we see that these two can share, and share. And that can share. And what we can see is that anytime we have two electrons between two atoms, they form a bond. So these, and these will all form bonds. Well, this is not in between two atoms, so it will not form a bond. And what we get is that right there. Okay. So what we see here, what we see here is these are our non-bonding electrons, and then these are our bonding electrons or our bonds. And in both cases, we see that they are in pairs. Now, we can have what we see here, which are single bonds. So a single bond is one pair of electrons shared between two atoms. If we share more than one pair, we get what's called a multiple bond. So a multiple bond is two or three pairs of electrons shared between two atoms. Okay, so if we have two pairs, this is called a double bond. If we have three pairs, it's called a triple bond. So we can see the double bond in something like carbon dioxide. So here are two lines. That equates to 4 electrons or 2 pairs of electrons. So our double bond. Our triple bond, we see this in cyanide. Right here. Here is our 3 lines. That equates to 6 electrons or 3 pairs of electrons. Okay. This is kind of just an overview, but let's look at how we actually draw our Lewis structures. So we're going to go through these steps to form Lewis structures. Okay, so what to be given is some sort of chemical formula, CH4, NH3, something like that, where you're given the atoms in there and you're told to draw a Lewis structure for those atoms. So our very first step is to find out what our electron pool is. So we're going to sum up the valence electrons from each atom in the molecule. Okay. Now, if we have an ion, we have to take that into account when we think about our electrons. Remember that if we have a cation, that means we have too few electrons, or we've removed electrons. If we have an anion, that means we've added electrons. So for a cation, you remove electrons equal to the magnitude of the charge. So if you have a 2 plus molecular ion, then you would take away 2 electrons. And then if you have a molecular anion, you add electrons. Equal to the magnitude of the charge. So if you have a molecular ion that's 3 minus, then you take and add 3 electrons to your sum or your pot of electrons, whatever you want to call it. The next step is you're going to write the symbols for the atoms, and you're going to take into account the atom connectivity. So you're going to show which atoms are attached to which. Okay, so what atoms are attached to what? This requires a little bit more explanation. So whenever you're given a chemical formula, generally the atoms are written in the order in which the atoms are connected. Excuse me, the atoms are written in the order that they are connected. Okay? And there are, most times for this class at least, there will be a central atom. So most of the molecules we will look at will have one central atom, where every other atom is connected to that central atom. The central atom is going to be the one that is least electronegative, with the exception of hydrogen. We exclude hydrogen because hydrogen is never a central atom. Hydrogen can only make one bond, and because it can only make one bond, it cannot have multiple atoms attached to it, therefore it cannot be a central atom. Please, 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 do not put hydrogen as a central atom. Okay, after you have written the central atom, you will put the other atoms surrounding the central atom, and you'll add lines connecting those atoms. So we will draw lines connecting the central atom with the other atoms, which are called peripheral atoms. So connecting the central atom to the peripheral atoms. Okay. Now, we have this pool of electrons, and now we've written lines. Those lines are electrons, so we need to subtract the electrons from our bonds from our pool of electrons. So subtract bond electrons. So the lines where each line is equal to 2 electrons from the electron pool. So it's the first thing we've removed from our electron pool. After we've done that, so step number 2 was very long. Next is step number 3. Sorry. We're going to complete the octets around all other atoms except for the central atom. So we'll complete the octets of the peripheral atoms. Again, we're going to exclude hydrogen from this. If we have hydrogen, it's good with just a bond. That gives us its 2 electrons. It is set. Again, subtract all the electrons you added from the electron pool. And then if you have any leftover electrons, you're going to place those leftover electrons around the central atom. And then you're going to keep doing this until you run out of electrons. If you find that you have run out of electrons and everything has an octet, you're done. If you, however, have run out of electrons and there are things without an octet, then you need to make sure that all of your atoms have an octet. So our last step, well, one of our last steps. So ensure that all atoms except hydrogen, boron, and aluminum, we have some exceptions, which I'll talk about in a little bit. So ensure that all of your other atoms have an octet. If you do not have an octet, you need to move electrons from non-bonding positions into bonding positions, making multiple bonds. There are other steps that I'll talk about in a little bit next lecture, but for right now, these are our general steps for Lewis structures. Okay, so let's try and draw the Lewis structure for silicon tetrafluoride. Okay, so first, our electron pool. So we have silicon, which has 4 valence electrons, and then we have fluorine, which has 7 valence electrons, and there are 4 of them, giving us 28 electrons. Sum them up together, we have 32 valence electrons. There is no charge, so we don't need to do anything to that pool. Our next step is going to be to write the symbols for the atoms. We have 2 atoms, so one of them is going to be a central atom, the other one is going to be a peripheral atom. If we look at our electronegativities, we will see that silicon, the one that's written first, and generally this is how those will work, the one that's written first is going to be our central atom, and then we're going to place the other atoms around the central atom, like so, and then add bonds in. Now, as we do this, hopefully you will see that we have added in 8 electrons, so we're going to subtract 8 electrons from our total to give us 24 remaining electrons. Okay, next we're going to add electrons to our peripheral atoms until everything has an octet. Right now, all of our fluorines have 2 electrons, so we need to add 6 additional electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. We are out of valence electrons, so we cannot put any electrons around our central atom. But if we look, silicon has 2, 4, 6, 8 electrons around it, so it has an octet. And each of our fluorines have 2, 4, 6, and 8 electrons around them, so everything has an octet. We are good. We are done with that structure. Okay. So, next thing we are going to talk about is the idea of a electronegativity difference. So electronegativity difference is differences in electronegativities between 2 atoms in a bond. So we already know what electronegativity is. Electronegativity, we are talking about when 2 bonded atoms, covalent bonds, have an unequal sharing of electrons. So we get an electronegativity difference when 2 bonded atoms share the bond electrons unequally. Okay? This occurs when one atom pulls on electron density more than the other. When an atom has a strong pull on electron density, we would say that it is an electronegative atom. Hopefully we remember our trend for electronegativity. It's going to increase in that direction. So fluorine has our greatest electronegativity. Something like cesium would have the smallest. We do not include our noble gases in this because these species have to have the ability to bond in order to have an electronegativity value. Okay, so if we have 2 atoms that are not the same, there's going to be some electronegativity difference between them, and no matter what, because no 2 atoms within the periodic table have the exact same electronegativity. There's some really close ones. And if we have an electronegativity difference that is very, very small, we would say that the electronegativity difference is small enough that we don't have an unequal sharing or that we have an equal sharing of electrons. So if we have a very small difference in electronegativity, we would say that the bonding electrons, let's go with the bond electrons, are shared equally. So this results in a non-polar covalent bond. And that small difference, so our difference in electronegativity, is going to be between 0 and 0.4 on a Pauling scale. I've added a chart of the Pauling scale electronegativities on your worksheet, so look at those. Or you could just look for an electronegativity chart on the Google. Okay, after that, we can have a greater difference in electronegativity. So a substantial, we'll go with substantial, difference in electronegativity would result in the bond electrons being unequally shared. We call this a polar covalent bond. So here we're looking at electronegativity difference that is greater than 0.4, but that difference also is going to be less than 2.0. So it's going to be between 0.4 and 2.0. Okay? So in this case, electron density is going to shift in one direction. So if we were to look at our two nuclei, and we're going to visualize the electron cloud, do that in blue works. And kind of look at it like this. So that would be an equal sharing, and there'd be no distribution in that electron charge. If we have a distribution where one atom, let's say this atom, has a greater electronegativity, we're going to pull electron density in that manner, or in that direction. So the electrons will spend more of their time around the more electronegative atom. Okay? And if we think about our atoms, they're neutral. So our protons and electrons are going to be equal to each other. So we're going to have a neutral species. Now we take a proton or a nucleus with protons, we pull electron density away from it, we produce a partial positive charge. That delta means partial. So we haven't had an actual removal of an electron from this species, but there has been electron density removed away from it, so we produce a partial charge. And then the direction it went, we used to have a balance of positive and negative. Now we've pulled more electron density towards it, so now we have a partial negative charge. These two will be equal to each other because we're pulling as much electron density. As we pull it from one direction to another, the one part becomes as positive as the other part becomes negative. Our last option is a significant, or a highly, we'll go with highly significant difference in electronegativity. In this case, the electronegativity difference is great enough that an electron will be transferred from one to the other. So, electron is transferred from one atom to the other. This results in a ionic bond. In order to get this, we have to have an electronegativity difference greater than 2.0. Okay? This brings us to the idea of a dipole. So a dipole is when we have charge distribution, so what we see here. So a dipole is going to be the result of electrons spending more time around the more electronegative atom. Okay, so we get these partial charges. We see that when we look at hydrochloric acid. Hydrochloric acid, hydrogen, has an electronegativity of 2.2. Chlorine has an electronegativity of 3.1. That gives us a difference in electronegativity of 3.1 minus 2.2, which is 0.9. Okay, so that 0.9 is greater than 0.4. So this bond that we see right here is a polar covalent bond. So instead of an equal sharing of electrons, like we would expect, we actually will shift our electron density towards a more electronegative atom, in this case chlorine. So it would look something like this. We would produce a partial negative charge on our chlorine, a partial positive charge on our hydrogen, and we would draw our dipole like this. As a note, this looks something like a vector, and it has magnitude and direction like a vector does, except for vectors, you write the arrow towards the positive instead of towards the negative. So a dipole will look a little different than a vector does. But it still has the same qualities. So a dipole is very similar to a vector in that it has magnitude and direction. However, it's going to be pointing in the opposite direction that you would see with an actual vector. Okay, so we can look at our electronegativity difference, and that will tell us a good idea about the charge separation within a molecule or within a bond. But we can actually calculate the value of the dipole moment with the following equation. U, which is dipole moment, well not U, U, is equal to Q, which is going to be our charge, or magnitude of charge, times by R, which is distance. In this case, this is going to be our bond length. So we've got our dipole moment, magnitude of charge, magnitude of charge, and then R is our bond length. It's also our distance. Okay. So we can use this equation to solve for our dipole moment, or if we have our dipole moment, we can also look at the charge separation. So looking at, or the magnitude of charge on each of our species. So if you solve for Q, you'll get a value. That value is the magnitude of charge on each of the species. Positive for the less electronegative or more electropositive, and then negative for the more electronegative or or the more electronegative atom. That's it. Okay. As a note, our dipole moment will be in Debye's. And then our Q is usually in coulombs. And then our R is in meters. Now, once we have our values in Coulomb and meters, we actually do need to get all of these into the same unit. So we will use our conversion from debye into coulombs, which will allow us to cancel that out. So if we have debye's, 1 debye is going to be equal to 3.34 times 10 to the negative 30 coulombs times by meters. So we can convert our debye's into coulombs when we use this equation, or we can convert our coulombs into debye's in order to use this equation. The other thing that we will see a lot of times with this equation is the use of the electronic charge. So the charge on one electron, or it could also be considered the charge of one proton. It just depends on the sign. If you have a negative to this, it's an electron. A positive is the proton, but I'm just going to give you the magnitude of it, which is 1.60 times 10 to the negative 19 coulombs. If this value is negative, we're talking about the charge of electron, one electron. If this is positive, we're talking about the charge of one proton. So putting those all in, we can solve for our dipole moment or our magnitude of charge. For instance, let's try an example. Let's say we have Hi, hydrogen iodide. Hydrogen iodide has a bond length of 1.61 angstroms. It has an electronegativity difference of 0.4, and it has a dipole moment of 0.44. Those values should be very, very similar. We could figure out the charge on both of our species by using this equation. So we want to go ahead and put our angstroms into meters. Remember that 1 angstrom is equal to 1 times 10 to the negative 10 meters. So this will be equal to 1.61 times 10 to the negative 10 meters. And then we want to put our dipole moment from debye's into coulombs. So we're going to take that 1 debye is equal to 3.34 times 10 to the negative 30 coulombs times by meters. And what we get is 1.47 times 10 to the negative 30 coulombs times by meters. And then it can all be placed into this equation. 1.47 times 10 to the negative 30 coulombs times by meters is equal to our Q times by 1.61 times 10 to the negative 10 meters. And we get a value of Q equal to 9.13 times 10 to the negative 21 coulombs. Now, this doesn't tell us a lot. We want this to be an actual electron charge. So we want to take this and convert it into our electronic charge, where E is equal to 1.60 times 10 to the negative 19. That E is that electronic charge. And this gives us a value of 0.057 E. So it's, if we had a full 1, we would have transferred an electron. But we did not, so we would say that our hydrogen has a 0.057 positive, and then our chlorine a negative 0.057 electronic charge on it. Okay? Okay, that really is it. And I will see you guys later.